All right, Lauren. It's time for us to start grading. 3.2a was supposed to be about everything to do with log equations. Not everything. I shouldn't say that. Everything to do with basic log equations. As far as what's going on with the base, as far as what's going on with some of them you can solve by hand, as far as reviewing some things to do with the properties of logarithms. Our goal today is to get into 3.2b and talk about their graphs. We talked about their equations. We just did some homework on their equations, and now we've talked about graphs. But let's keep grading. So number 2 was supposed to be 10. Number 8 was supposed to be -2, because we can make 81 9 squared. Remember, we want the bases to match. But the problem is the 9 squared was in the denominator. What kinds of powers go in denominators? Negative. Good. So it had to be a -2, not a +2. You were going from logarithmic to exponential, from exponential to logarithmic. We might add one little baby thing in our notes from 3.2a about those forms, because some of you might just want to memorize how to go back and forth. Even though it's good to understand how a logarithm works, maybe for some of you it's easier just to memorize. So we'll try to write that down today. What's going on with the 1/2 power again? How does this work? 25 square rooted. Good, good, good. Just making sure. 1/2 power is a square root. So 5 is the square root, or the 1/2 power of 25. 10 is, well, wait, hold on. A common log has a base of what? 10. Remember the cheater calculator trick? If you do second common log, what's the power that pops up? 10. Yeah, it's a cheater trick to remember. Common log, 10 to what power is 10? Well, 10 to the 1. Yeah, exactly. So some logarithms, if you get better and better at what a log is and how he works, maybe you can go a little bit faster. On the ones that are nice numbers, the ones that are nasty decimals, I don't think we can do those in our heads. This used, do you guys remember, we wrote it down quick yesterday. I think some of you guys took pictures of them. Do you know the name of the property that lets us say 9 to the log 9 is just going to be what's up above, or just 15? Say it a little bit. Actually, it's for logs and exponentials. So good idea. It's not the logarithmic. Close. The 1-to-1 is when we have 1 here and 1 here, and they match. So we can ignore. There's one more. There's the 1-to-1 property, and there is one more right below it called the... Can I give you a hint? It's undoing each other. Undo, undo, undo. Undo. Come on. What kinds of functions undo? Are their own undoing. Inverse property. It's an inverse property. Inverse. Oh, wait. That was it? Okay. Doesn't mean it was super easy, but those were the only evens from last night. I have it ready. What do you talk about? Okay. Did we get, I'll give one more chance just in case you guys have a question. But did you get down those properties? They're super important. We just referred to, Priscilla mentioned the 1-to-1. I mentioned the inverse property. Even though you guys took pictures, even though it was on the video and in the notes, just real quick, if you didn't get the properties down, get them down, highlighter, color pen. Just because, remember, we're developing the skills to face the harder puzzles, the harder levels later. Speaking of puzzles, what's due today? The harder Sudoku reflection. So let me give you a second. Go ahead and get the reflections out. But I also want you to make sure you have the properties down. So I'm going to give you time for both. I want you to get the reflections out, the properties down. Let's not pass up the reflections quite yet, just because I want to go over the answers. I want to go over the answers. Okay, we should have had time. Let's go ahead and talk about those reflections so we can get them passed in. Talking about puzzles, talking about harder puzzles. In order to face the harder puzzles, you do need to know the fundamental, like what are the rules, what's the point of the game, etc., etc., etc. But you also have to have some practice. That's why I gave you like a very easy puzzle the first time. That was the one we turned in yesterday. This one was a little bit harder. I think it still was technically an easy one, but it wasn't a very easy one. However, I don't know, the brain teasers on top were kind of hard, if you guys didn't figure out the trick to it. First one, what'd you guys get? Looking down on the stack of whatever those are. A. Nice, it is A. Because you need a lot of light, a little dark, and a little light. A lot of light, a little dark, and a little light. If you look at it really closely, there is like a light outer rim. Letter A is the only possible answer. The second one, it is impossible to add 3 odd numbers and get an even. So what did I mean yesterday when I said you're going to have to think outside the box, or at least look at it from a different perspective?
6 plus 11 plus.
Yeah, the 9 does not have a line under it like the Uno card. So the 9 could have been turned upside down to be the 6. Dun, dun, dun. So you could do 6 and what, 11 and 13? Yep. So you had to turn the 9 ball upside down, or maybe the 6 ball right side up. Plus 11 plus 13. Struggle. Sudoku, did you guys fill it in? Okay, real quick, check with people in your group and see if it matches. Yesterday, remember, we weren't quite ready for that. Go ahead and compare. I think some of you guys already did. And if someone in your group doesn't have it done, turn to the other groups. And if you've been absent, you can sneak it in probably on Monday, and I won't mind too much. Oh, you didn't get it? We filled in a few yesterday, right? We filled in like a 2 and a few 1s. Okay, if it's something where you're like, I don't like Sudokus, find a friend that does. I bet there's at least a few friends that are like, oh, we'll do it with you, for you. In ASB a couple days ago, we had a few ASBers working on the same Sudoku because they messed up a couple times. Anyway, find a friend and do it with them. You don't have to do it alone. It's all right. But still, it's a fun puzzle. So if for any reason you weren't here on the day of the test, I'll give you till Monday. But the rest of you guys, you've had a lot of time. Let's pass it on up. Make sure your name is on it. Let me get those reflections from you. And let's get back to section 3.2b. Properties should be written down by now. You guys don't need to make a new section in your notes unless you want to, because we already wrote down the title with an A and a B. Logarithmic functions and, that's fine. Makes more sense too, huh, Lauren? So you guys don't have to make another section of notes. You can just keep going. Technically, we already put graphs in the title of 3.2. I just kind of split it up so that you guys would know what was necessary for the homework yesterday. All right, real quick. Anybody absent? Chris Massey's gone again, right? That's it. So as you guys can tell, we're talking about graphs today. Very similar to what we did with exponential functions in 3.1. We talked about their equations first, and then we talked about the thing here. We're going to talk about their equations first, and then their graphs. We have our last person taking our test on Monday. And I'm hoping I'll then have your guys' test graded and ready to go. My goal this weekend is to get your Run Web updated. I think we're about halfway through the next grade, so you can see where it's at. It's a little while to get another test in. And then with the retreat, it's taken me a little while to get it finished as far as graded, but try to get that in for you guys to know where things stand. And if you're missing anything, to double check and make sure I have all your grades too. I know a few of you guys are doing makeup work in Google Classroom, which is good from being absent or being injured, etc. Just make sure to put a comment to remind me of what's going on as to why something is late. If it's a few minutes past 7, you're probably okay. I know sometimes loading pictures takes longer than you want it to. So if it's a little bit past 7, it's usually okay. I still count it as full credit. Sometimes I put an excuse, sometimes I just give you full credit. But a few of you guys are kind of consistently getting it in quite a bit after 7, meaning like 7:30, 7:45. We need to shore that up just a little bit. As far as I don't want to be making you late to school every morning because you're posting your homework way late. Okay. It is warm in here. All right. It's okay. I'll stop complaining. Here we go. Logarithmic functions, the graphs. Back in section 1.6, we talked about parent functions of parabolas, x squareds, of absolute values, absolute value of x, of square root of x. Swoop, there it is. Of what else? X cubed. Of the step function. He's awkward. Of what else did we talk about? Is that it? Oh, 1 over x. He was our last one, right? Okay. And for each of the parent functions, for each and every one, I showed you guys representative points, like key points, to each graph. And then if you guys go peek at section 3.1, real fast, go look at it. Section 3.1, go find me the graph of the basic exponential function. Literally, flip back. I should see pages. Flip back, 3.1 is only the last section or 2 sections back. Find me the graph of an exponential function, okay? I'm going to put them up here on the board just for reference. I want to know from you, what are the key points of the exponential function? Y equals, what did we say? A to the x? Okay, a to the x. What's one point of that? Because if you plug in 0, anything to this, we talked about 0 allowed to be in the exponent base. Negative numbers aren't allowed to be, but anything to the 0 power besides 0 is going to be 1, right? What's the next? When x is 1, what happens anytime x is 1? It's just the base, whatever the base is. Who is he? I don't know. Maybe he's 2. Maybe he's 4. Maybe he's, okay. Whatever he is. It'll be 1 comma a. And what's the other representative point? Negative 1. And if you raise a to the negative 1, you guys have the table, right? That's going to be a to the negative 1 or 1 over a, which is going to be somewhere down here, some fraction guy. So I could do negative 1, 1 over a. And then can't you guys hopefully see your swoop? There it is. What's going on the x-axis for exponential functions? Okay. What was the property that Priscilla and I were hashing out, trying to figure out at the beginning of class with homework questions that you guys just wrote down if you didn't before, showing the relationship between exponential and logarithmic? Inverse. Wait a minute. Inverse functions, what's going on with their graphs? Careful. Across. Not this, not this. Anti-asymptote. Y equals x. That's the line. And do you remember with inverses, doesn't something switch with inverses? Reflect across the y equals x line. What switches? The x's and y's. So guess what? We have everything we need for our logarithmic graphs from our exponential graphs. Because every single key point of the exponential is going to become the key points of the logarithmic. For instance, instead of 0, 1, it's going to be 1, 0. Instead of 0, 1, it's going to be 1, 0. We'll make a table in a second. But instead of 0, 1, it's going to be 1, 0. Instead of 1a, it's going to be, not the steak sauce though, but a1. Does anyone even use that anymore? You do? I like Sweet Baby Ray's a little better. But anyway, 1a, or barbecue sauce, becomes a1. But we don't know who A is. It depends. 5 is, so we'll get over here somewhere, okay? Whoever A, sorry. Okay, whoever A is, it's going to go up to 1. And then the point -1, 1 over A is going to flip again to be 1 over A. I'm not quite sure where that is, but -1. Okay, some fraction-y thing down here. -1. Nope. Sorry, I did not flip it. 1 over A, -1. Why? Because they're inverses, and inverses flip. The domains and ranges switch, the x's and y's switch. That point was just kind of ugly, sorry. Give me 1 sec. That's better. Do you guys see the swoop? Swoop, there it is. Which should make sense, hopefully, because over here, if we reflected for the inverse, wouldn't it make sense? Going the other direction, right? Now, if an exponential function has a horizontal asymptote, we're going to have not horizontal. That's what the exponential had. What's the logarithmic one going to have? Sorry, my bad. Instead of y equals 0, it's going to have x equals 0. And if you guys were looking at that exponential graph in 3.1, you would have seen he had a horizontal asymptote, which means this guy is going to have, here we go, a vertical asymptote. Exponential functions have domains of all real numbers, forever left, forever right. So logarithmic are going to have ranges of all real numbers. They flip. Exponential had a range of 0 to infinity, which becomes the domain of logarithms. So everything just switches. Where you just were in your notes, the exponential, his range became the logarithm's domain. And where you just were in your notes, exponential's domain became logarithm's range. Oh, I already showed you the guy over there. Y equals log base A of x. I didn't write it up here, though. And all of this is because they're inverses of each other. But we can make a little baby table, too. That's not a bad idea. Just like we did with exponential. Plugging in some key points. Let me do it in red. So it's kind of like we're just playing around with the function. So where our key points come from is ones to plug in would be 1 over A, because that's a nice easy power of A. Well, not easy, but possible. 1 is a nice one, because any base can go to the 0 to get 1. And then A is a nice one. A to what power is A? Well, that's just 1. And A to what power is 1 over A? That's -1. But some of you are like, I'm kind of starting to be able to do mental math with nice logarithms. Some of you are like, yeah, no. That's okay. To be honest, every key point of a logarithm is exponential, and it's a lot easier to find his main points and then flip for some of you than it is just to outright find the points yourself. Wait, we missed something. What's the x-intercept? Good. Oh, not 0, 1. Sorry, careful. It flips. 1, 0. The x-intercept, not y. Strictly monotonic. You guys remember that, right? The really teacher who just talked like this the entire time. Monotone. What did that mean for exponential? What was strictly happening? Right. So what's this guy doing? Yeah, he's actually increasing just like the exponential is, in the sense of they're both increasing, but he's going way slower. As exponential increases faster and faster and faster, logarithm or logarithmic functions increase slower and slower and slower and slower. All to do with that inverse relationship again. And just like exponential functions, he's also continuous. And you're like, wait, but he has a vertical asymptote. I know. He's continuous. Put it in parentheses. Everywhere on its domain. It's not continuous apart from its domain, but everywhere inside it's fine. No breaks, no holes, no vertical asymptotes on the inside. But we do have to talk about his domain problem. Remember, back in section, I don't even know what it was. Chapter 1. I have no clue. That's okay. We talked about domain problems. Denominators can't be 0. Radicands, what's under the radical, can't be negative, so greater than or equal to 0. And then I had logarithms in parentheses. It's time. Here we go. Logarithms. Log base a of u. Doesn't matter the base. Any logarithm, including ln. Whoever's on the inside, the domain says that must be greater than 0. All because there's a vertical asymptote at the argument equal to 0. If it's just x, no big deal. X is greater than 0. X can't be 0, aka the vertical asymptote is at 0. Like this guy. But if you were to have like x plus 1, well, x plus 1 has to be greater than 0. Oh, so the asymptote is at x equals negative 1. Anyway, whatever's in the logarithm, that entire argument must be greater than 0. That's how we find the domain. And the vertical asymptote will always be at the 0 of the argument. If I were you, I would grab out a highlighter, I would grab out a colored pen, I would make a note of that. Because domain problems, we're going to be accumulating them throughout the year. And that's one of those big topics that isn't bound to a certain chapter or a certain section. It kind of comes back time and time and time again as we introduce more and more. Oh, where's my highlighter? As we introduce more and more functions, like when we get into trig, we'll have to think about domain also. So domain, we just kind of keep building on. So I'd make a big point of that one, okay? All right. You guys got them? A couple more seconds. A few of you guys are doing the colored pen highlighting thing. But let's talk about just like we did with exponentials, okay? So if we have a parent function, stuff can change. It can be transformed. I didn't do all the possible transformations, but here are a few, just like I did with exponential. We can be adding on the outside of the logarithm, aka vertical. What's adding? What kind of transformation? I'll give you a second to get down the basic transformed logarithmic function. In Algebra 2, you would have called them G, because your original would be. That's just a name. So now that we have a parent function for a log, now we can transform them. And just like we did with exponentials, we can transform, taking each of the individual. We have A1. And our vertical asymptote at x equals 0. Has anybody caught up to the blank I was filling in? If we're adding b, what kind of transformation is that? Adding b, not multiplying by b. Multiplying by b would be a vertical stretch. Yeah, translation. Simple way, short way, shift, but good, translation. Why did I have to ignore the person who said horizontal? It's on the outside. Outside is vertical, affecting the y's. Inside, let's find the horizontal shift. Inside, subtracting, adding, that's where he is, right? I don't make a big deal with the stretches and the compressions, even though they can happen. Because if I start bringing in other, like, oh, hey, let's make them a D, and oh, hey, let's make him a, just so many letters going on. So there could be vertical stretches right here multiplied by the log. There could be horizontal stretches or compressions in here multiplied by the x. But I'm just going to go ahead and put the base as another possible way of transforming. If the base gets bigger, you can look at the graph if it helps. If the base gets bigger, instead of going out 2 or out 4 or out, ooh, the more the base increases, what happens to my poor little log graph? Yeah, kind of a horizontal stretch, which ends up doing what to my curve? It gets slower. So if A gets pulled, just think of a rubber band, it's going to get flatter. But it gets smaller, like 1/2 or 1/3, which rarely ever happens in the logarithm, but it would get steeper then. But reflections, we remember this one. Reflections, if you have across the x-axis, can you guys visualize that? Is that horizontal or vertical? Does that make sense? It's the vertical axis. Oh, wait, x-axis. Silly me. You guys were right. Where's the x-axis? Now it's randomly yellow. Okay, that's new. Okay. My bad. I went across x equals 0. Around the x-axis is around y equals 0. What kind of flip is that? What's up is down, what's down is up. So that's a vertical flip. And since it's vertical, where's that multiplying by a negative going to happen? Outside or inside? Good. Outside the logarithm? It's going to have to be multiplied outside the logarithm, which could actually become a power of, okay, I'm getting ahead of myself. That's section 3.3. We'll see it when we get there. And across the y-axis, I mean, if you guys are pattern people, you know it must not be vertical, so it must be horizontal. If it's horizontal, we're multiplying by a negative on the inside, which only a couple of you might be like, ding, 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 not allowed to have negatives. I know. Which means the only possible domain must be negative numbers, so that a negative times a negative is a positive, aka instead of going for positive x's, it's going to flip and go with negative x's instead. But anyway, negative on the inside will flip that logarithm over. Negative on the outside will flip that logarithm up. So to that end, guys, let's play with some graphs and see if we can do it. What logarithm do I have waiting for you? Log base 2. Can you guys go ahead, look at the board or look at your notes? Can you set up the graph of log base 2 of x using the key 3 points that we talked about? Now, what's your base? 2. So make the graph specific. Make the graph specific to this log, okay? I'm going to do it too, but I go really fast sometimes. So look at your basic 3 points, plug in, A is 2, and then graph. Do you guys agree with 1/2 negative 1 and 0, 1? Sense? 1 over base 2. Negative 1. 1, 0, and then who? 1? A, 1, 2, 1. There we go. There's our 3 representative points. Here's our starting vertical asymptote. And here's our swoop day. Oh, sad day. Here's our swoop day. It is. Is that good? Okay. What else do we have besides F? G. All right. What's G? So if you want to think about it in terms of what's going on, 2 up, aren't all the f's, y's going to add 2? And aren't all the f's, x's going to, what are they going to do? Add 1, right? So in a vertical shift, the y's add 2. And a horizontal shift to the right, all the x's add 1. So each of these y's, up. And x plus 1. And I will at the point 1.5. Right? Adding 1 to the x and adding 2 to the y. Got it. Adding 2 to the y, up 1, up 2. Adding 1 to the x. which would be the point, 2, 2. 2 to the y. Did I do it backwards? I did it backwards. Adding 2 to the y and 1 to the x. Oh, do you guys see that I wrote my point wrong? That's not 0, 1. What point is that? Silly. 0. I wrote the exponential point. No wonder that was so weird. There we go. So 2 and adding 2 to the y is 2. My 2, 2 is right, just my silly point was wrong down there. There we go. The x, 2 to the y. This guy too. Add 2 to the y. He's now at y is 3. Add 1 to the x. Going to have 3, 3 to the y. Where's my vertical asymptote? That'd be super nice to have. What happened to him? If he moves up 2, does anything change? No. But then he moves right 1. So if I can get my vertical asymptote at x equals 1, oh yeah, hey, it's the 0 of the argument, right? X equals 1, then swoop, there he is. Got him. Got him, coach. Right there. Took each of my points and I shifted them both up to right 1, including my vertical asymptote, and it gave me a nice little guide for where to swoop. But help me, guys. What happened in the last one? What happened in the last one? There is going to be a flip down. You could say down. You could just say vertical flip. That's this guy, right? Multiplying by a negative on the outside of the logarithm. There's a vertical flip followed by what? Translation. Careful. I know there's a minus, but that's multiplying by the logarithm. What sign is in front of the 1? A positive. So where's it shifting? So if you want to think about it from the original graph, my y's are going to have to be opposite and have negative y's that need to add 1. My y's will all become opposite and then add 1. So for this point, 1/2 negative 1 is now 1/2 positive 1, and I add 1. Well, that's weird. And that's going to be the point. The x stays the same, but the y gets flipped to be a negative positive 1, and then plus 1. That's 2. Who else do I have? This guy. 1, 0 needs to vertical flip. Well, that's boring. He doesn't go anywhere. But then he also needs to be shifted up 1. So then he's going to be the point. 1, 1. The y adds 1 after flipping. Negative 0 is still 0. Plus 1. Okay, there he is. Then this guy, 2, 1, his y needs to flip signs. So 2, negative 1, and then add 1, which is going to be 2, 0. 1 times a negative is negative 1. Negative 1 plus 1 is 0. Where's my vertical asymptote? I vertically flip him. Well, that's boring. I go up 1. Well, that's boring. Did he go anywhere? Vertical asymptote. I flip him, and I go up 1. Still the same, right? So, do you guys see the swoop? Could this be hard if you don't use your 3 representative points? Yes. I think so. It's a little bit harder of a graph to deal with. So get your 3 main points. Whatever base they give you, you can get your 3 main points. And then think about step by step, how are the y's changing, how are the x's changing, and don't just move your points. Also move your vertical asymptote because it helps you know where the swoop goes, okay? Transformations of logarithmic graphs, totally possible. Start with your main 3 points right back here. Start with your main 3. Figure out what are the transformations to the horizontal, vertical, to the x's, to the y's, and don't forget to move your vertical asymptote, and this shouldn't be too bad. So here's a quick reminder, and technically we wrote it on the board. Maybe some of you guys already wrote that down, but if you didn't, you can go ahead and write it down now. Quick reminder of the graphs of exponentials and logarithms put all together. Quick reminder of when you put it all together, the exponential and the log. They just did an example. They did 2 to the x and minus 2. If you like mine on the board better, because it's general, you can use a to the x and log base a, which can change based on They just gave you a specific example. I gave you a general idea. Both ways work. But it probably is a good idea to get it down, just to remind you guys of what's going on. There's the exponential swoop with its 3 key points. They put way more than 3, but I think 3 is enough. With 0, 1, negative 1/2. Sorry, negative 1, 1/2, positive 1, 2. They went by 2s, which is kind of awkward. So in some ways, I kind of like my graph on the board better, but if you want to plug in 2s, that's okay. But just writing down real quick. Across the y equals x line, which means x's and y's switch. So if you ever forget the key points of a log, just do the exponential guy, and then switch, 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 and you've got it. If you ever forget the log and his key points, just find the exponential guy, his inverse, and then flip, 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 and you got it. Reflect across the y equals x line, x's and y's switch. You guys okay with the picture on the board? Able to use that if you're still going? Okay. Try it out, cool kids. Hopefully after homework last night, this one's going to be easy. Because as you do section 3.2b, there might be a couple equations that come back. Mostly it's math, but there might be equation-y things too, logarithm. Especially with ln's and e, don't work with them much unless you're in like chem or physics or dealing with radioactive decay or working with compounding interest. You might not see e very often, or you might not see ln very often, so I'm trying to make sure that you guys don't get scared of them when you do see them. Y equals ln of x, when x equals e to the negative 4. Any mental mathers already have an answer for me? Yeah. Wait, what? No, we have to take that and plug it in, right? And where do we plug it in? Isn't this way worse than negative 4? Y equals ln of e to the negative 4. Ln is log base what? Yeah. So if you want to rewrite it, you don't have to rewrite it, but you can rewrite it. Remember, every logarithm answer is what power? E to the negative 4 is what power of e?
Negative 4 powers of e.
But the inverse property that we talked about multiple times today also says log base e undoes the e to the power of. Not that I want you guys crossing it off or crossing it out, but it is the idea that in essence they do disappear and the negative 4 remains. So maybe you can even do some logarithms mental math style. Guys, that's homework 19, section 3.2b, and we're done like 7 minutes early. Pause. I want you guys to write down the first page of section 3.3 notes. But as you guys do that, I'm going to go ahead and go get section 3.2b homework so that you guys can, with a little bit of extra time that we have in today's class, get it written down in your homework spiral number 1. Who knows, maybe you'll have extra time in a class today to bust out your math homework. But then also, if there's time, maybe even pull up the homework section themselves or itself so that you guys can even start. Of the month, today's the 19th. Is that what you mean? Friday, October 19th. If you guys are thinking about skipping lines, all you have to skip is just enough space to fill in the change of base formula that we actually already know. Hopefully. That we actually already know, hopefully. The next homework is number 20, right? Yeah. So all you need to skip space for is the change of base formula. Technically, you could probably throw it in really quickly because we already talked about it. You can change the base of any logarithm with a quick division. Those of you guys with yellow buttons on your calculators, it's the only way to plug something like this in. It's kind of a bummer. But we're going to use that starting tomorrow to talk about properties of logarithms. That really unlocks the door to what we can do as far as solving puzzles that are coming. But that's going to be on Monday. For right now, here we go. If you guys want, you can write down homework number 20, what the problems are. You guys can write down homework number 20, what the problems are. Starting with number 37. You have about 5 minutes still, so I have the book ready to go. I can project on the screen. Some of you guys might already have your books at your desk. You can grab them out. I say, why don't we just go ahead and get some homework done, huh? It's a good way to spend a Friday. I'm going to show you guys numbers 37 to 40.